All right, so welcome to the first chapter of social network analysis. And in this particular chapter, we will talk about what do we mean by social network analysis. We will formally define what we call as network and why social network analysis is important. And I'll try to motivate you guys why these days social network analysis is an important research area. And hopefully you'll be able to understand the importance of this course at the end of this lecture. So I must thank all the all these lecture materials online which are available online, from where I have taken some of my slides. Most of the slides are very descriptive. I wanted to make it descriptive so that you just read the slides and understand the content. But if you still want to go deeper into all these concepts, please feel free to look at this book. And this book is available on Amazon and Flipkart, and the Kindle version is also available. So how many of you feel that you are a part of a network? Okay. In fact, if I tell you that you are part of multiple networks, right? How many of you feel that you are part of multiple networks? Can you guys tell me? You can unmute and tell me. How many of you feel that you are part of different networks? So being a part of networks, right? Oftentimes you feel some sort of attraction, some inertia or pull from different networks, right? So if you tell me that you are not a part of any network, you are basically lying, right? Because I'm pretty sure that at this moment when I'm delivering this lecture, some of you maybe opening your WhatsApp and chatting, right? So some of you maybe calling your friends or family members. Some of you are browsing internet. Some of you are talking to your colleagues or family members. So all of these constitute networks that we are part of in our daily life. For example, in WhatsApp, you can consider WhatsApp as a giant network where these users are different nodes, and when you send a message to another user, you can see a link, right? Similarly, when you call somebody, you can think of a link from your side to your friend's side, right? Similarly, when you browse internet, you can again think of some sort of network activities going on, where a packet from one computer to another computer, or one computer to a router to another router, is basically moving, and through which you can create a network. So these are all online networks, right? In offline also, you can think of networks where when you say interact with your family members or your friends, you can consider creating an edge, right? And this is called social interaction network, right? Where nodes can be social agents or entities, and links can be formed in different ways. For example, see, if I say that two users or two individuals talking to each other quite frequently, you can create an edge between them, right? Now these kind of offline networks are very important to study, say for example epidemic, right, or contagion, right? So when I use the term network, sometimes people think of network as a computer network, right? A basic TCP/IP protocol, right, and so on and so forth. I must say that computer network is definitely a network that we are talking about, but this is not the only network that we are talking about. This is basically an example of network that we'll talk about in this course. Similarly, when I talk about network, people sometimes think of neural network, because these days this is the buzzword, right? Again, neural network is an example of network that we study, but this is not the network. This is not only the network that we'll discuss here. Okay. So now, what is network? Network in general is a simple abstraction of a complex system. Okay. Now I have used the term complex systems. I will discuss what is complex systems. Okay. In other words, sometimes people define network as a general language or a generic language for describing a complex system. Okay. So these definitions may sound a little vague, right? Because what do I mean by a general language or abstraction, right, is not very well defined. I will try to define it mathematically in the next slides. Okay. So in general, if you see, complex systems, the complex systems can be our human body, where, if you go deeper into the mechanisms of our human body or any animal's body, you see that protein interacts during the metabolic process. And then again, you see interactions between cells, genes, and so on. And all this, the entire dynamics can be thought of as a complex systems. Similarly, think of World Wide Web, right? World Wide Web, you have hypertext, you have different, web pages, and web pages are linked through hyperlinks, right? So if you think of the entire World Wide Web, you won't be, it's so complex that you won't be able to understand how things happen in World Wide Web in general. Okay, so these are all complex systems. So complex systems are often abstracted or often modeled using networks, right? So network is often called as a simple way of representing a complex system. Okay, so network is also known as graph. We computer scientists call this as networks, but physicists call this as graphs. Okay, it is also known as complex networks. Now, why it is called complex networks? What is the complexity behind it? We'll discuss about it later. Okay, but in general, these kind of networks, the kind of network that we'll talk about in this course, are so large, right? That some of the phenomena, some of the topological properties are not that simple. For example, let's take an example of a simple graph. For example, a line graph. Okay, we all know what is a line graph. So this is a kind of a line graph or chain graph, right? Or a star graph like this, right? Or a complete graph like this, or a clique like this. Okay. Now these graphs are simple graphs because the properties are trivial, right? But think of a network like Facebook network, right? Where we see, trillions of users, trillions of connections between users, and these connections also evolve over time. Some connections get added, some connections get deleted, nodes get added, nodes get deleted. The entire phenomenon is so dynamic, right? And it is, and the entire dynamics is also temporal, right? So you won't be able to use regular, graph theory kind of tools or properties or theorems to analyze this graph. So therefore, these kind of graphs are called complex networks, right? Because these networks exhibit non-trivial topological features that do not occur in a simple network such as lattice or random graph. Okay, now what is random graph? What is lattice? We'll discuss these things later, right? But you assume that, the simple graphs like lattice, random graph, a line graph, a star, a clique, right? These have trivial properties, and such trivial properties can be analyzed very easily using traditional graph theory approach. Whereas, social network or typical biological network or, protein-protein interaction networks, these networks are so complex that you may not be able to only use graph theoretic properties to analyze those. So therefore, there is a need of a separate thread of research, separate branch of science, which only deal with understanding the structural and functional properties of these networks. And this is called network science or complex networks in general. So now, when I talk about network, what is it? It is basically, a collection of nodes, right? Or collection of entities or agents or vertices, right? There are different names, different nomenclature that people use, right? And the connections between nodes, right? Now you see here, I have used different colors to draw nodes and edges. Now, what are the meanings of different colors? So these colors may indicate different types of nodes or different relations between nodes, right? For example, in case of Twitter, right, nodes can be users, nodes can also be tweets or posts, right? Nodes can also be groups, right? In Twitter also you can create groups, right? Where links can also be of different types. Say, for example, in Twitter, links can be follower-following link. A link can be created if someone has replied to someone else's post, right? A link can be a link can represent a reply. A link can represent a follower-following. A link can also represent a like, right? There's a post, there is a user, and the user has liked this post. So you can create a link between user and the post. And this link indicates the like relation, right? So most of the real networks are heterogeneous in nature. I will discuss about it later, but heterogeneous in the sense that nodes can be of different types, links can be of different types, relations can be of different types. So that's the reason I use different colors to indicate different nodes and different edges. Okay. So now this is the basic definition of network, more of a formal definition. A network is represented by an ordered pair G, V, E, G, V, E, where V is a set of nodes or vertices, and E is a set of edges or links. Okay. Now this is a very simple definition. You can also make it complicated by adding, attributes of nodes, attributes of edges, relation types, and so on and so forth. But this is a very simple way of defining a network. Network can be of different types. Undirected network, where there is no link between there is no direction of the link, right? For example, this network, you see there is no link, there is no direction in the link, right? It's called undirected network. And similarly, you can have directed network, where you see that there is a direction from one node to another. So undirected relation, you can think of it as a kind of you can think of it as symmetric relation, where there's a typo here. It should be symmetric, right? It's a symmetric relation because the relation between A and B and the relation between B and A are same. Whereas in case of directed network, say, follower is a directed network, right? Because if I follow you, it is not necessary that you will also follow me, right? So therefore, directed link is an asymmetric or irreversible relation. Okay. And now, depending upon the data that we collect, the situation that we have, we basically model the data using that kind of network, right? Say follower is a directed link, whereas friendship relation is an undirected link. Okay. Links can be also of weighted in nature, right? Say, for example, in this case, you see that there are weights associated with edges, and these weights indicate certain properties. For example, say, again, in a friendship network, for example, this link weight, the weight of the link can indicate the number of times you have chatted or you have sent messages to the other friend, right? Again, this link in case of Twitter network can indicate number of times you have shared the post of other user, you have liked the post of other users, and so on and so forth, right? In case of social network, you can also think of these weights as amount of traffic, that the number of packets that are moving from one router to another router, or one computer to another router, right, at a particular time, for example, right, as a weight. It can indicate the load, entire traffic load. So edges can be also edges can have self loops, right? For example, if the two endpoints of an edge are same, right, you can basically see a loop like structure here. So this is basically a self loop or a loop. Okay. Similarly, parallel edges, if there are there are multiple edges between a pair of nodes. These edges are basically parallel edges. Okay. So these are some of the basic definitions that we will use throughout this course. So now, what is social network analysis? So network, we have seen, it is basically an abstract representation of relations among entities, right? Social network is a simplistic representation of a social structure, right? Now, this can be an online social network like Twitter, Facebook. It can be an offline social network like user-user interaction network. Sorry, I mean the individual interaction network, person-person interaction network, right? And social network analysis is basically an application of networks and graph theory through which we analyze different relations, different patterns of a society. It can be online society and it can be offline society. Okay. So now this is a typical, Twitter, sample Twitter network that was drawn way back 2014. And you see already it is so complex, right? You can't analyze the properties of this network by just looking at it. Okay. So you need certain tools, certain mechanisms, certain theorems, properties, right, by which you can analyze the entire network in general. Okay. So what are the basic what are the kind of domain knowledge people require to understand social network in general? We assume that those who work in this area have fair bit of ideas about sociology, psychology, mathematical theory, statistics, and computer science, right? So that they would be able to understand the interactions, quantify the type of interactions, the measure certain properties of networks, measure the interaction dynamics between two nodes, and so on and so forth. Okay, now let's look at some of the applications that we generally study in social network. So particularly in healthcare, right? I have already mentioned that offline social network, individual interaction networks, right? You can, if you have, say, let's assume that hypothetically, that who is connected to whom, who frequently meet whom, right? So there is this interaction network available. Let's assume that. Now, when we study the some epidemic outbreak, for example, say COVID-19 again, right? And that okay, these individuals have already been infected, okay? And we also know that how these individuals interact, right? We have this contact trace, right? So through which we can predict that, okay, these are the set of users who are going to be infected tomorrow or day after tomorrow. These are possible vulnerable users or individuals, right? Similarly, now if you predict it, you can also think of, isolating them, or, planning for a, better way of imposing lockdown and identifying the vulnerable population, within the society who you should vaccinate first, right? So that the remaining part of the network become safe, right? So, planning for effective vaccination, planning for isolation strategy, lockdown strategy, and everything can be calculated, can be done very effectively if you know this contact network. Okay, and there are studies in the past which basically showed that how many such epidemic outbreak could have been stopped if you had contact network beforehand. Okay. Social network, of course, in general, as I already mentioned multiple times, right? Say Facebook social network or Twitter social network. If you think of, so, we have seen all this, friendship recommendation, friend recommendation, or, follower recommendation every time in our timeline, right? So you may wonder how, how a particular friend has been recommended for you, right? So friend, you have no contacts, for example, since last 10, 15 years, but suddenly one day you see that his name has popped up, right? And you may wonder that how Facebook has come to know about this friend, because you may have forgotten about him or her, long time back. Now we'll see during the course that how these friendships are these friends are recommended by different social networks, right? We will also identify different propagation patterns of information, right? Let's say again, hate speech or fake news, misinformation, certain propaganda, right? Political propaganda, how political propaganda spread on social network, right? Is it random, or there is some mechanism through which this propaganda are being spread, right? And we will see that there's a clear distinction between how a propaganda is being spread versus how a normal information is being spread, right? Say for example, if you were told to promote your event, right? You were told to promote certain agenda. So what do? So the first thing that may come to your mind, that let's contact some big shots, right? Some celebrities, for example, say Amitabh Bachchan, Shah Rukh Khan, and let them promote your event. And you all know that if those guys promote your event, that would automatically attract attention. But convincing people like Amitabh Bachchan or Shah Rukh Khan to promote your event is not straightforward. You need money, right? So now it basically boils down to an optimization problem, where you already have a certain budget, right? And given that budget, you know that, okay, if I convince this user, you basically need to give this amount of money, right? If you convince that user or that individual, you can. So given the budget, how you can optimally optimally convince individuals in social network to promote your event or to promote your propaganda. Okay, this is again something that we'll discuss in one of the chapters. E-commerce services, we all know how e-commerce platforms like Flipkart, Amazon, they recommend items to you, right? And this recommendation system, the whole idea of recommendation system is basically stemmed from the graph analysis, graph mining in general. We'll discuss in one of the chapters that how say if you buy mobile phone, for example, why you are suddenly you are recommended a Kindle, for example, again, right? So if you buy bread, why you are recommended a ham, for example, right? So we will discuss all these things in one of the chapters. Again, web search is one of the important functions that we use in our day-to-day life. Google search, Bing search, back days, Yahoo search, and so on. So you all know that the search engine is basically operated on a graph, on a massive graph called World Wide Web, right? And the concept like PageRank, right, that was invented way back 1998, 2000 by the Larry Page and Sergey Brin, and they started their company. I'll tell you the history of PageRank, the algorithm, right? This algorithm was rejected. This algorithm was a part of one course project at Stanford, and the idea was rejected initially. 2 years back, it got published in World Wide Web, and the rest is history. So the entire World Wide Web network is analyzed through social network analysis techniques, I mean graph mining techniques in general, and all the web pages. Whenever we use keywords to search web pages, right, the way web pages are ranked by social network, right? So there are different graph algorithms running behind it, and based on that output of those algorithms, you see the ranking of web pages in different search engines. Cybercrime and terrorism, this is again a very important application of social network analysis these days, right? So we all know the online fraud, fake news propagation, cyberbullying, trolling, right? Spread of offensive content online. So these are all kind of adversarial activities that are happening on social network. And if you model network, if you model social media as graphs, you can easily see that how fake news propagates, how you can stop, how we can come up with ideas to stop the spread of fake news, offensive content in general. There is another interesting study happened way back, I think 2010, where they studied that how 9/11 attack would have been stopped if we had this kind of terrorist network designed beforehand. Right now, terrorist network basically constitutes nodes as terrorists, and two nodes can be connected if two terrorists say were arrested together, or two terrorists went for a similar mission, right, somewhere and arrested. So this kind of interaction, terrorist interaction network, through which you can, there are studies which showed that you could have very easily stopped the attack of 9/11 by identifying some of the key agents in this network if we had this network beforehand. Okay. Another very important applications of social network analysis is to understand how science evolves. Okay, how research evolves over time. So we all know that when we write a scientific paper, we cite other papers, right? So you can clearly see a directed link from citing paper to cited paper. Okay, so this is called citation network between papers. Similarly, when researchers collaborate, right, you can also model it as a network. It is called collaboration network, where nodes are researchers and two researchers can be connected if they have collaborated before in any project or any paper, right? So if you look at this citation network or collaboration network, you can clearly see how science evolves over time, right? How one idea from one particular group of people move to another group of people, and suddenly these 2-3 ideas again merge and form a interdisciplinary research, and so on and so forth, right? You can also recommend potential collaborators using say collaboration network. You can recommend important literatures using citation network. So this has a lot of applications in bibliographic research in general, scientometrics research in general. So network is generally represented by metrics. It is called adjacency metrics. We all know, right? Where the dimension of this matrix is n cross n, where n is the number of nodes present in the graph, right? So if the network is undirected, then you see a symmetric matrix, and if the network is undirected, you see a symmetric matrix, and if the network is directed, you will see an asymmetric matrix. Oftentimes, this matrix based representation is not efficient because of the sparsity of the graph. So when you have this million cross million matrix, right, all these gigantic matrices, you see most of the entries in this matrix are 0, right? So therefore we generally use adjacency list to store the graph in general, and we all know what is adjacency list. So basically we have a list of vertices, and for each vertex we store, using a linked list, we store nodes which are connected to the given vertex. For example, here node 2 and node 3 are connected to 1, so like this. Similarly, node 1, so node 1, 3, 4, 5 are connected to 2, so you can create a link from 2 to this set. Now this is the neighborhood set of this particular vertex. Okay, now this is efficient representation because of the sparsities. So now let's look at different network types. Okay, so when we look at a network, there are different views of a network. So let's look at link-centric view. Okay, so in link-centric view, there are different types of networks. So one is called Unipartite Network. In Unipartite Network, it's just a simple network of set of vertices and set of edges. Okay, where there is no restriction between connections, restrictions on the connections between nodes, right? On the other hand, there is another type of network called bipartite network. Okay, in bipartite network, you see there are two partitions of vertices. Okay, you see these green nodes and these brown nodes, right? And the constraint here is that within a partition, nodes should not be connected. Okay, so you see here, green nodes are not connected with each other. Brown nodes are also not connected with each other, but across partitions, nodes are connected. This is called bipartite network. Example of bipartite network, e-commerce network, right? Users and products. So users can, when a user has bought some product, you can create an edge between user and product. But in India, at least, I don't know whether it is not allowed that a user buys another user. Again, a product cannot buy another product. So you can't create an edge between among users. You can't create an edge between products, but you can create edge from one user to another product. Right? This is a clear example of bipartite network. Similarly, you can have tripartite network, multipartite network, and so on and so forth, depending on the problem again. The network can also be of signed network. Okay. Now, what is signed network? In signed network, a sign, a positive sign or negative sign or neutral sign is associated with the edge. Similar to weighted network, where weight is associated with an edge, here a sign is associated with an edge. Now, what is the meaning of this sign? The signs, positive sign indicates friendship relation, and negative sign indicates animosity, right? There are websites like Opinion, Slashdot, where you explicitly mention that these users are my friends and these users are my enemies, right? So then when you model that platform as a network, you see that sign, right? If one user explicitly mentions that the other user is an enemy, then the link is negative, otherwise positive. Similarly, trust network, for example, right? So if you trust me, then there's a positive link. If you distrust me, then there's a negative link, right? So sign network is again very important to study how social ties, right? We'll discuss later balance theory, status theory. We'll see there, this signs are very important to understand the stability of a certain portion of a network, right? Say, for example, if there is a link, if there is a structure like this, say minus, right? Minus, right, and plus, say A, B, and C. What does it mean? It means that A and B are A and B are enemy, and B and C are also enemy, but A and C are friends, right? So, right, and this kind of structure is very stable because look, so since B is a common enemy of both A and C, therefore it is highly likely that A and C would be friend. Okay, this is this comes from a social science theory in general. Okay, so this kind of structure, studying this kind of structure is very important in social science in general. We'll discuss. Now let's look at a different view. So far we have looked at link-centric view. Now let's look at node and link-centric view. Okay, so when you look at both nodes and links, there are again different types of networks. So one is called homogeneous network. In homogeneous networks, all nodes are of same type and all links are of same type. Okay, standard simple network. For example, follower-follower network. All nodes are users and all links indicate follower-follower relation. Heterogeneous network, nodes can be of different types, edges can be of different types. So sometimes nodes can be of same types, but edges can be of different types. So it is, then that kind of network is called edge heterogeneous network. Sometimes node can be of different types, but edge can be of same types. This is called node heterogeneous network, or both node and edge heterogeneous networks. Right? I have already given an example. Twitter, for example, users can nodes can be users, can be posts, links can be follower-follower, retweets, likes, and so on. Okay. Attributed networks, nodes, a network can nodes can also have attributes. For example, in Twitter network, for example, you have often seen that user describes himself or herself using some text, right? Say a faculty, researcher, politician, and so on. So these are the attributes: the age, gender, job, and so on. These are the attributes. Nodes can have attributes. Ages can also have attributes. Say, for example, if the age indicates a message, for example, right? So the body of the message is the attribute of that age. Okay. So you see here, this is an attributed network of students, where this attribute of students indicate different departments and colleges, right? And you can use attributes in different ways, right? This is even more richer information of a network. Similarly, you can model it as a multi-dimensional network, right? Or multi-layered network, where you can think of each relation as a layer, right? Say, for example, there are, let's say, in a platform, there are two layers. One layer indicate follower-followee relation, another layer indicate retweet relation, right? So follower-followee relations happen exist between users. Retweet also relations exist between users. So in both these layers, node set is same, but the link sets are different. Link types are different. So you see, most of the heterogeneous networks can be modeled as multi-layered network or multi-dimensional network. Okay, where each layer indicates a dimension. A local view of a network, there is a terminology called ego-centric network. Now, what is ego-centric network? Ego-centric network is a small subset of a network where there is an ego or a central node, and there are peripheral nodes which are directly connected to the central node, one hop connection. Okay, please remember, this is one hop connection, direct connection, right? And these one hop connected nodes, these nodes are called alters. So these are alters, and this is ego. And we also look at the connections between alters. Okay, now this is called ego network of this node. So what is ego network? Ego network is an induced subgraph of the ego and its alters. What is the induced subgraph? Induced subgraph means the subgraph that can be sampled, that can be collected from the original network, where the edges between these nodes, between these egos and alters, between the ego and the alters, are taken from the original network, right? So if in the original network, say for example, these two nodes are connected, in the ego network also this should be connected. Okay, so ego network is ego network of a vertex V is an induced subgraph of the vertex, of that vertex and its one hop neighbors. Okay, its alters. Similarly, we have temporal network, where network changes over time at different timestamp T0, T1, T2. You see, some nodes get deleted, some edges get deleted, some edges get added, and so on and so forth. So most of the social networks are, the temporal network. More general, if you look at, a general type of network, you generally use something called hypergraph. Now, what is hypergraph? In hypergraph, there is no concept of edge. There is no concept of link. Okay. So instead of link, we use something called hyper edge or hyperlink. Right. Now, what is hyper edge? Hyper edge, say for example, in normal edge, two nodes, an edge can connect only two nodes. But in hyper edge, an edge, and that hyper edge can connect multiple nodes. Okay. For example, say let's assume a collaboration network. Okay, scientific collaboration network. Now these are the researchers who have written a paper together. So this edge, this hyper edge connects these four collaborators. Similarly, there is another paper written by, say for example, these three researchers. This is another hyper edge, right? And look at these two hyperedges. They are connected by this node, right? And these hyperedges can also be can also have weights, right? If these 4 researchers write multiple papers together, right, then you assign some weight here. So the weight is 4, right? So this is a more generic way of representing a graph in the form of hypergraph. Okay. So some of the popular real world networks that we study include social network, like email message network, social academic co-authorship network, biological network, protein interaction network, food network, genetic regularity network. Information network includes World Wide Web, citation network. Topological network includes power grid network, electric power grid network, internet, railway network, airlines network, and so on. Similarly, language network, you can think of also language, as networks where, where there are persons, and 2 persons can be connected if they speak in same language, for example. Or say, nodes can be languages, and 2 languages can be connected if both the languages are evolved. Both the languages evolved from the same language, for example, right? Say Hindi, Bengali, all these languages evolved from Dravidian language in general, so you can connect them together, right? So now we basically discuss about different levels of view, right? For example, when you look at a network, either you look at nodes and edges individually, right? Or you can look at the network as a whole, right? Or one may also want to look at different substructures or subgraphs of a network, right? Subnetworks of a network. Now, depending upon the kind of labels through which you want to view the network, right? There are 3 different levels, right? One is called microscopic level. In the microscopic level, what we do, we generally look at, nodes and edges separately. Okay. And so, I mean, basically we look at the interactions between nodes, and depending on that interactions, we have this different levels of interactions. One is called dyadic level of interaction, where interaction happens between 2 nodes. Okay. Similarly, we look at triadic level of interactions where the interaction happens between 3 nodes. Okay. And when we say 3 nodes, essentially, it may form a clique, a triangle like this, or it also can form structure like this. Okay, where you see here, this is a dyadic level interaction. This is also a dyadic level interaction, but as a whole, this is a triadic level interaction. Similarly, egocentric circles that I mentioned, right? Ego network is also kind of microscopic level of microscopic view of a network. When we look at the entire network as a whole, it's called macroscopic level, macroscopic view. Okay, so we basically measure different properties of a network as a whole. For example, average path length of a network, diameter of a network, edge density of a network, right? So say diameter of a network, we all know diameter of a graph is basically the longest shortest path. Okay, so we take all pairs of nodes, we measure the shortest path between each pair of nodes, right? And then then you have shortest paths for all pairs of nodes, and then you take the longest one, the largest one, and that's the diameter, right? So diameter is a view of an entire network. It's not a node-centric view or an edge-centric view. Similarly, edge density. So edge density is essentially, we'll discuss in the next chapter, but so roughly speaking, edge density is the actual number of edges present in the network divided by the all possible edges that can be formed in the network, right? So this is edge density. So again, it's a property of a network. It's a property of an entire network. So macroscopic view is basically macroscopic view talks about the measurement of entire network as a whole, whereas microscopic view basically talks about measurements for nodes and edges. Okay, so in between macroscopic and microscopic, there is another level called mesoscopic view, right? So in mesoscopic view, you basically look at different substructures of a network. Okay, for example, cliques. Say, for example, communities, right? Now, communities we'll discuss in one of the chapters is that we oftentimes in real world we see that similar kinds of nodes interact with each other and form a dense subgraph. Okay, now these dense subgraphs are called communities or clusters in the graph. Okay, now when you look at a community, this is not an entire node network centric view. Neither neither is it a node centric or eccentric. This is basically a subgraph centric view. Okay, and this is called mesoscopic level. Similarly, we'll discuss in another chapter called something called network motif, right? Now, network motif is basically recurrent substructure, right, which appears repeatedly in the network. For example, if I say that what are the possible network motifs with say with 4 nodes, right? So you see here in this case with 4 nodes, you can come up with all these different structures, all these 6 structures, right? One looks like this, which is a star. Other looks like this, which is a chain. This is called a 3 loop out because you see a loop here with 3 nodes, and other edges out of this loop. This is called box. This is semi-click, and this is click. So network motif, given a set of vertices, given a number of vertices, the possible substructure that you can draw out of those vertices are basically your motifs. Okay. Similarly, say if I ask you that what are the network motifs with nodes 3, right? You can come up with structure like this or this. Sorry, this, right? This is a chain or a click, right? So these are the motifs with node 3, and these are the motifs with node 4. Similarly, you can have different combinations if you have more number of nodes, or 5 or 6. Now, these motifs are often called as building blocks of a network, right? Oftentimes there are research which actually showed that number of stars, number of chains, distribution of motifs across different networks oftentimes presents the characteristics of the network. For example, there are studies which showed that if you look at the co-authorship network, for example, nodes are researchers and 2 researchers. If 2 researchers have collaborated together, you can create an edge between them. This kind of co-authorship networks, right? These network motifs indicate that, say if you have a co-authorship network and you count number of star motifs, chain motifs around a particular substructure, particular ego network, for example, right? And it would give you a lot of it would give you a lot of evidence that this co-author is going to be highly popular, and this co-author is not going to be popular in that sense. So network motifs, again, particularly in biological domain, it has a lot of significance. Okay, we'll discuss it in the later class. So you see here, community structure, network motifs. These are not the entire node-centric view, network-centric view, nor is it a node-centric or eccentric view. This is in between, right? Therefore, this view is called mesoscopic view of a network. So microscopic, macroscopic, and mesoscopic. So what are the common properties that we generally observe in real-world networks? Most of the real-world networks are small world network. Now we'll discuss what is small world network. Essentially, it says that the world is not so large. If you see the average path length between a pair of nodes, it should not be more than 6, right? There is a very famous experiment happened long back 1980, 1985, based on which this phenomenon called 6 degrees of separations was proposed, and I will discuss this in the next class. And this basically resembles the small world property of network. Similarly, we'll see that most of these networks follow something called power law degree distribution, And power law in general, property-wise, it's a scale-free network. So those networks which follow power law degree distribution are scale-free. We will also see that real-world networks form clusters and communities quite often. It is rare that networks do not form many clusters. So because of this property called homogeneity, right, nodes with similar properties interact quite often and create these clusters. Okay, we'll discuss this. Most of these networks, we will also discuss the property, something called robustness to random node failure, where say you have a network and you try to destroy the network structure, or you try to destroy the community structure in a network. Then how would you remove nodes or edges from the network so that the community structure gets disrupted, right? What would be the attacking strategy to disrupt the structural property of a network is something which we'll also study. Cascading effect is also, again, very natural. What is cascade? So when an information spreads over network, it basically creates a cascade. Say, for example, I tweet something, you retweet my tweet, and one of your followers retweets your tweets, and so on. So you see there's a chain, right? And it may create a chain. It also may create a tree, right? Say, for example, I post a tweet, two of my followers retweet that tweet. Again, their followers retweet that tweet, and so on. So you can see a tree emerging from a seed tweet, right? And this is called cascading effect. This is also related to virality, prediction, information diffusion in general. When we study cascading effect, we also study something called the how vulnerable a particular network is, or a set of nodes are to particular cascading failure. For example, there is a power grid, okay, right? Electric power grid, and if one of the nodes gets disrupted for certain reason, right? It should not happen. It should not happen that effect gets propagated to the other nodes, right? If it happens, then the entire network gets disrupted over time. So how would you design the network, right? Optimally design the network so that your network is not that vulnerable to this kind of failure. Okay, particularly this is very relevant for power grid kind of network, where if a particular power station fails, right, to supply electricity, it should not happen that the rest of the power stations also get disrupted. Okay. So we'll discuss all these things in all these properties in this course. And now you may ask why social network analysis is so important these days. So the major reason is the amount of data that we receive every day. Okay, if you look at the history of social media, right? So in 1996, there's something called Bolt, which was there. This was one of the first social networking video website. Then we had MySpace and so on and so forth. But if you look at the number of usage of social network, right, around 50% of world's population is active on social network in 2020. Okay, and we have seen the advent of social media like Facebook, YouTube, WhatsApp, Instagram, WeChat, Tumblr, TikTok, Reddit, Twitter, Pinterest, right, Snapchat, and whatnot, right? And the amount of data that we are getting every day, right? It not only gives you like the freedom to design systems, design different models for the social network, but also gives you ample opportunity to understand how users or how individuals behave or interact in the online setting. Okay, and that's the reason most of the social networking companies are becoming so popular these days because of this data. So the applications of network science in general, we use it for node classification or node coloring problem. For example, say there are user networks, right? And the task is to identify which users are fraud users, for example, right? So fraud versus genuine. Now this is a node classification problem. Link prediction is a very important application in social network. Now, link prediction can be used for friend recommendation, for recommending advertisement, for product recommendation in e-commerce services, and so on. Predicting the virality of a product, right? Predicting the virality of a message, of a post is very important. As you clearly understand this, I mean, on Twitter, we see trending topics, and trending topics are nothing but the viral topics, right? If we analyze social network, you would also be able to identify important nodes or prestigious, prominent nodes in the internet network or certain communities, right? And if you identify important nodes, that can also help you again, you know, in say personalized advertisement, right? Or it can also help you, you know, spread some message, right? And so on. Social network is also used, you know, the traditional sampling method that we used to use for data mining in general. Most of them do not work because here, you know, here the nodes are not sampled, or the data points are not sampled from IIT, right? So basically here nodes are dependent on each other. There are connections between nodes, right? So sampling technique has also evolved for networks. And therefore, you know, we'll discuss in other chapters that how network sampling happens, and how, I mean, oftentimes, you know, we don't have the capacity to access, you know, to analyze billions of nodes in a network. What we do, we sample networks, and then we basically test our model on the sample network, and then we upscale our application on the entire network, right? So sampling is very important. Information spreading, as I already mentioned, right, says is misinformation, hate speech, fake news, right? We need to stop them, and therefore we need to devise mechanisms to stop the spread of such harmful content. Anomaly detection also is very related to, you know, misinformation spread, etc., where anomalous nodes are those nodes which are very different from the normal types of nodes in the network. Okay, so identifying anomalous nodes may not always be the case that is, you know, these anomalous nodes are harmful or bad actors or bad nodes. Anomalous nodes, for example, would be exceptional researchers in co-authorship network, for example, in citation network, exceptional papers. Okay, so anomaly detection is again a very important problem in network science in general. There are many other applications that we'll study in this particular course. Okay, so with this, I would like to stop here. You know, and let's hope that you, at the end of this course, you would learn the skill of networking. Okay, thank you.